So in the previous discussion, we have seen that we started with an interacting theory, and we said that this be the Hamiltonian. This is for now onwards. These are all operators, so I will not add some thought. So this is the free part of the Hamiltonian. This is the interacting part. This is the full interacting theory Hamiltonian. And we said that let omega be a state, which is the state of, which is the ground state, that is the state of minimum energy of the full interacting theory, and let this be the state, ground state of the free theory, and this is a time independent Hamiltonian. Therefore, we have this to be equal to E naught omega and H naught this. And for this full interacting theory, both capital omega, that is the ground state, minimum state energy of the Hamiltonian H, and the eigen minimum, the ground state energy, both are very difficult to calculate. And what we are interested in calculating is the following vacuum expectation value of the time order product of two field operators. And these are field operators in the Heisenberg representation because they are time dependent operators. And we want to calculate such a quantity. And in this calculation, it is very difficult to calculate this because we don't know what this is, what omega is, and we also don't know what this field configuration phi is, because it is very difficult to find out a proper expression for this field operator phi, right? Because this is in the field which evolves, which is in the Heisenberg representation, and therefore it revolves by the full Hamiltonian. Therefore, it is very difficult to find an exact expression to write down mean mathematical expressions for phi x. So, in principle, this is a difficult quantity to calculate, but we need to calculate this quantity. And for that, what we did in the previous discussion was that we tried to find out an expression for phi x, said that phi x, this x is a 4 vector, so it includes time and x vector. So this phi x is related to I by h bar Hamiltonian e by 0 x to the power of -i. So this is how phi is related to the field configuration at time t is equal to 0. So this is the field configuration at time t is equal to 0. And we also introduced the interaction picture field, which evolves via the free Hamiltonian, and that is, so this also you can write as x for vector, and this is equal to e to the power of, since it evolves, this is not h naught, this is h, sorry, this is h. So this field evolves via the full Hamiltonian of the interacting theory h, and the interacting field Hamiltonian phi naught, this evolves via h naught, and that is this. And then in the previous class we showed that we wrote down phi 0x in terms, we wrote down this phi 0x in terms of phi naught x. And if we do that, what we got was phi t x vector, you can write it down as u dagger of I think this was t or minus t, let me just check. It's t, which we found that this is u dagger of p, dagger p, and then we had phi 0 t comma x, then we have u of, where u has the standard representation that we have already seen, that the standard form. It is basically e to the power of I by h bar h naught t, e to the power of minus I by h bar h t. That is the form of u. So in this way, we managed to relate the field, the Heisenberg, the field in the Heisenberg representation that we want here, that is sitting here, managed to relate this field in terms of the interacting field operator. And U, this thing we know also evolves via the interaction in the interaction picture. Okay, this is what we have seen already, and we have also seen the following. Let me go to the other side of the board. We have seen that you can relate. So, e to the power of I h t. We started from this thing, and then we worked our way. We said that let n be eigenstates of this full Hamiltonian H. Then what we did was we introduced complete set of states, and then this became this. Then we isolated this n is equal to 0 term. To do that, then you will get this n is equal to 0. We said that this n is equal to 0 is basically nothing but omega. This n is equal to 0 term. So that is the ground state of the full interacting Hamiltonian, which is time independent state. This time independent. So you have omega and omega 0 plus, then we had summation n not equal to 0, and then we have some terms. And then we took the limit t going to infinity into 1 minus I epsilon, took this limit, and in that limit, all these terms fall off, and we get this ultimately comes out to be. So if you replace this small t by capital T, then this becomes a capital T, this becomes capital T, and we have omega 0. So this is what we get. And from here, we managed to write down an expression. We wrote down an expression for. So this we have already done in the previous class. Is omega becomes limit t tends to infinity into 1 minus I epsilon. Then we have e to the power of minus I by h bar Hamiltonian t 0 divided by some factor. Some factor means this part, this thing, and this part. This omega and 0 overlap. And Shom was asking that. Shom, are you here?
Yes, sir.
Okay, you were asking that how can there be an inner product between these two, because H has this Hamiltonian has a Hilbert space and H naught has a different Hilbert space. But the point is that both these Hilbert spaces are infinite dimensional, right? These are infinite dimensional Hilbert spaces. And in the previous discussion, we also mentioned, you just recall the single harmonic, the single particle harmonic oscillator, the quantum harmonic oscillator, and there also you have it's a free harmonic oscillator. So that Hilbert space is infinite dimensional. You put in an anharmonicity that is also infinite dimensional. Therefore, states in both these Hamiltonian, the free Hamiltonian or the interacting Hamiltonian, they are both states to belonging to infinite dimensional Hilbert spaces, and therefore there is no problem in defining inner product between them. Okay, so is basically this, and this number is basically the power of that factor divided by this overlap of omega and 0. And from now on, we shall just write it as a tilde and omit that number for the time being. And we shall write this as limit t tending to infinity into 1 minus epsilon, where epsilon, let me remind you, is approaching 0 from the positive side, so epsilon is a small positive number. And this is e to the power, you can introduce e to the power of I by h bar h naught capital T, because h naught acting on 0 is 0, so that factor will be 1. And therefore, if you introduce here e to the power of I by h bar h naught into capital T, this full thing is nothing but u of u dagger is I h naught minus, so u dagger will be ut is e to the power of I square h naught t e to the power of minus I by p square ht. So if you take a dagger, what will happen? This will become h and this will become h naught, right? And therefore, if you put a minus here, this will become plus and this will become minus as a base. So this is nothing but u dagger of minus t. So what you can write is this omega is nothing but, apart from these numbers, it is u dagger of minus t 0. Okay? So this is the relation that we found in the previous discussion. I just summarized it for you once again. So if you have any doubts here, you can ask once again. If you have any questions or comments about this expression, then you may ask at this point. So what we see that we see is the following. We want to know what this state is, this omega, because we have no clue about what this is. But now what we have managed to do is that we have managed to relate the ground state of the full theory, interacting theory, to the ground state of the free theory. And the relation is through this evolution operator, u dagger. And u dagger, you know what this is. It is basically this u dagger, this u operator basically evolves via the interaction part of the Hamiltonian in the interaction picture. So you know what this is. And then you have to take the limit t going to this thing. Okay? So this is what this thing is. You can once again start, similarly, you can start from this thing to the power of this. You take the dual, the bra 0 to the power of this, and you take limit t going to infinity into 1 minus I epsilon. You can do the same thing here. And if you do the same thing here, you will end up, if you just compute just by introducing complete set of states and all those things that we have done, you can show that bra omega will be limit t goes to infinity into 1 minus epsilon bra 0 u of c. That is what you will get. You just follow the same steps as I've just done for this get omega. You do it for this thing. You will get the relation between bra omega and bra 0. So we know what these things are. So now we need to calculate this full thing, and we shall do that now. What we need to do is just substitute get omega and bra omega here. So we shall put a tilde because we are neglecting the numbers that are there in the denominator. We are not writing those numbers. So we shall put a tilde here and just write down this expression. So this bra omega is basically, so you should remember that you have a limit always standing outside this thing. You have this limit, and then this bra omega is bra 0 u t. Then you have this time order product. So what is this time order product? So let us see what this is. So what we shall do is, before calculating this, what we shall assume is that let x naught be greater than y naught. Let x naught be greater than y naught. Then this time order product, basically you can remove the time order t from here. This is already in time order form. The other term is 0 due to the theta function. Let us assume that x naught is greater than y naught, and since t goes to infinity, therefore t is obviously greater than x naught, and y naught is obviously greater than minus t because t goes to infinity. Okay, so we have ut, then we have pi x. Phi x we shall write it down as, so we have an expression for phi x. Can you tell me that expression? That expression for phi x is basically nothing but it is u dagger. This is x. The time here is x naught, so this is u dagger x naught. Then we have phi naught x. Then we have u x naught. This is just phi x, this part. And this part was bra omega. Let us put phi y now. What will be phi y? Phi y is phi y will be u dagger of y naught phi 0. This is the interacting field. The field in the interaction picture. It evolves via the free part of the Hamiltonian. So this is phi naught y, and then we will have u of y naught. So this part is nothing but this is phi y. This is phi y. And then we have ket omega. What is ket omega? Ket omega is u dagger minus t 0. So this is the full expression for this condition. We have this condition, then we have this expression. Is it okay? We have just substituted everything what we had calculated earlier in the expression for this propagator. So this is equal to, once again, limit t goes to infinity into 1 minus I epsilon. This is always there. Now what we shall do is, so once we have written down this expression, now if you take a time modeling, now let us take a time modeling. So what will happen? If you take a time modeling of both sides, then there will be a time modeling here also, right? There will be a time modeling. Now, inside the time modeling, you can actually move the operators as you like, because wherever you can put the operators wherever you like inside the time model, because ultimately there is some time ordering operator sitting outside that will time order, that will take care of the time model. So what we can now do is the following. I can take this operator and put it here, u x naught, and put it on the left hand side of phi naught x. And then what will happen? U dagger x naught, u x naught. U is an unitary operator, therefore that is identity. Therefore what we shall get is time order of ut phi 0 x. Similarly, I can take this and put this over here. No problem. Inside the time ordering, I can put the operators as in any position. So once again, u dagger y naught, u y naught, this will be identity because u is unitary. Therefore, I will have only phi naught y, then u dagger of minus t, then 0. There is a time order. So this is what we have. Now, again, I can take this ut and put it over here inside the time ordering. If I do that, then this will be limit to infinity into 1 minus I epsilon bra 0 time order of phi naught x, phi naught y, and u dagger minus t. What is that? It is basically e to the power minus I by h bar integral minus t to plus t v I t prime dt prime. Then VIT is basically the interaction part of the Hamiltonian in the interaction picture. Okay. So this is what we have. So this is up to some factor. This is up to some factor. So we can take care of that factor in a nice way. If you just divide throughout by omega omega. So that will take care of the normalization. So you calculate this overlap omega omega. What is this? This is nothing but, again, up to a factor. This is ra 0 u dagger u of t, and this is ket is u dagger of minus t 0 with limit, obviously t goes to 1 minus this, and this expression is nothing but this limit is there. This is there. This is 0. This thing is once again minus t plus t 3I t prime g prime. There is no need to put a time order. You can put a time order, but these are already time ordered expressions, and t is a later time than minus t. Therefore, this expression will be this, right? So that is fine. You can put it there. You have to put a time order technically because these are operators. So this is a time order, this is a time order, and therefore this will be time ordered product of this. Here I didn't put a time order because the time ordering is already sitting outside. So there is a time ordering outside. Here we need to put a time order. This is this. So this is your omega omega up to some factor. So you can get rid of the factor by just saying that you can get rid of the factor, the unwanted factor, by considering the quantity this by this. So if you consider this quantity, then this will be nothing but, now the unwanted normalization factor will get cancelled from the numerator and denominator, because here also you have the same factor and here also you have the same factor, and you are dividing it by these two, so that factor is now gone. Therefore, this quantity divided by this quantity is nothing but limit t goes to infinity into 1 minus I epsilon, where epsilon goes to 0 plus, this is nothing but this time ordering of phi naught x I y to the power this divided by so this is a very important formula that we have now proved. This formula tells you that a propagator or the probability amplitude for a field or a particle to propagate from a time, say y naught, to a later time, say x naught, in the vacuum of the interacting field theory, is basically given by this expression. So you can see here that in the right hand side, this quantity is equal to this. In the right hand side, you have things which you know, for which you can write down mathematical expressions. These are free field operators or operators in the interaction picture, and therefore they evolve via the free part of the Hamiltonian H naught. This you know. So you know the normal mode expansions for these fields. The normal mode expansions are valid for this. For this, the normal mode expansions are not valid. But for this, the normal mode expansions are valid. You know this part because this is also the interaction in the interaction picture. So that means that it basically evolves via the free part of the Hamiltonian. So you know what this is. So you can calculate this, and you know also what the denominator is. So you can calculate you can calculate this thing by using this formula. The right hand side, everything is known. So you can in principle calculate this. So this is a very important formula. This is a machine by which you can calculate quantities like this for an interacting theory. And then there is some theorem which is known as Wick's theorem. Wick's theorem. So before discussing Wick's theorem, let me just mention another thing. This is also quite important. It basically tells you that this result is actually valid for any product of operators, time ordered product of operators. If you have, say, phi x1, phi x2, to phi xn, and then take time ordering, this will just become phi not x1, phi not x2, phi not xn. It is valid for any string of operators. So what we need to know is we need to know how to calculate time ordered products of operators, a hat of a string of operators. So in order to calculate now the problem of calculating this quantity has boiled down to the problem of calculating this quantity. That is the time ordered product of free field, the vacuum expectation value of the time ordered product of free fields. So this is what the problem has boiled down to. And therefore we need to calculate time objects like this. And not only that, the vacuum expectation value. And this vacuum is the vacuum of the free theory. That is what we need to calculate. This vacuum is the vacuum of the free theory. And this is the vacuum expectation value of the time ordered product of interacting fields which evolve via the pre-Hamiltonian. So we need to calculate quantities like this. And if you can calculate quantities like this, then you know what the right hand side is. So this is what we need to do. And it turns out that to calculate quantities like this problem itself is a difficult problem. Because calculating vacuum expectation value of time ordered products is a difficult problem, and we know what this is. We have seen what this is. For free fields, obviously these are free fields. These phi naughts are free fields. And we have seen what this is, what this vacuum expectation value is. We have already calculated in some previous lecture, a couple of classes before. And this was nothing but the Feynman's operator for the real scalar field. We have already calculated this. So let us now see that in principle how to calculate vacuum expectation value of a time ordered product of a string of operators. And the way one does it is by making use of the theorem which is known as Wick's theorem. So let us do it. Just a remark before looking at the Wick's theorem. This theorem, you should remember that this theorem works only for free fields, not for interacting fields. For free fields, the theorem works. But what about interacting fields? This theorem does not work. But that is not a problem, because for interacting theory, this object you have actually written down an expression in terms of free fields. And now you can apply Wick's theorem. So that is the strategy. So let us see what Wick's theorem is. As I mentioned that even calculating the vacuum expectation value of a string of operators, where the string of operators are all free fields, is a difficult task. But calculating This is not difficult. The vacuum expectation value of the normal ordered product of a string of operators, string of free field operators. Can anyone say what this quantity is? Can anyone tell me what this is? What this second quantity is? This quantity is 0, right? Because this is a normal order of the operators. So in normal ordering, you know that all the annihilation operators will be on the right hand side of the creation operators, and therefore the annihilation operators will annihilate the vacuum, and therefore this is identically 0. So the idea is the idea of this theorem, which works for free fields, is to write down time ordered product of a string of operators in terms of normal ordered product of a string of operators. If you can do that, then your job is done. Then you can actually calculate. So let us do that now. So before that, what we shall do is we shall break an operator a hat in terms of two parts. What does A plus stand for? A plus stands for the annihilation part of this operator. The annihilation operator. You remember the mode expansion for phi. There is A and A dagger. A plus A dagger. So there is an annihilation part. There is a creation part. A plus stands for the annihilation part. A minus stands for creation part. That is our standard nomenclature. And similarly for B also I decompose in the same way. And let us now calculate what A hat B hat is. Let me calculate what A hat B hat is. So A hat B hat will be A plus. So I'm not writing hats anymore. Let me just omit the hat notation. These are all operators. So remember that there are hats on top, and this will be B plus B minus. This is AB. Now this will be A plus B minus plus B minus A minus. Okay. Now if I take a normal order of this thing, what will happen? If I take a normal order, then this will be again A plus B plus, because there are no creation operator here, both are annihilation, so it will remain the same. This is already normal order, A minus B plus. The creation operator is on the left hand side of the annihilation operator. This term is not normal order, it is normal order. It is A plus B minus. Therefore, the normal order form of this will be B minus A plus. And this is already, there are two creation operators. Therefore, this is already, you can write in any form you like. Okay. Now, let us subtract NAB from AB. So if you subtract it, what we shall get? This term will cancel. This term will cancel. This term will cancel. Therefore, you will get this is equal to A plus B minus B minus A plus. Therefore, this is equal to nothing but A plus commutator of A plus and B minus. Is this okay? Are you okay with this?
Yes, sir.
Good. So let me now do one thing. Let me put some arguments here. Let me write this as AX dy. Okay.